Good afternoon, everyone, on this beautiful fall afternoon day. I'm Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, the Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar. We're grateful to the Ministry of Labour for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. The presentation of today's webinar will be as follows. The presentation will be given, after which time we will have approximately 10 to 15 minutes for your questions. We ask that you type your questions into the chat box, and I will relay these questions or their themes, should there be duplications, to our presenter. Should you have a pressing question that cannot wait until the end of the presentation, such as a technology glitch, please type this into the chat box and we will do our best to address it right away. We do record these webinars and make them available on the CRE-MSD website down the road. We will be also providing you with a copy of the presentation after the webinar, along with an evaluation that we encourage you to complete in order to assist us to plan the future delivery of our webinars. Now it is my pleasure to introduce to you today our presenter, Dr. Nick Delfa. Nick is an assistant professor in the Faculty of Health Sciences at Ontario Tech University in Oshawa, Ontario. He completed his undergraduate and graduate studies at McMaster University under the supervision of Dr. Jim Potvin, with a focus in occupational biomechanics and proactive ergonomics. When he then completed a postdoctoral fellowship at the University of Waterloo, where he trained with Dr. Clark Dickerson, CRE-MSD's Assistant Director of Research in the areas of clinical and occupational shoulder biomechanics. The overall objective of Nick's research is to reduce the prevalence of work-related musculoskeletal disorders through the advancement of our knowledge of human capability, function, and performance. Nick's basic research evaluates the capacity of the human body to perform work. Specifically, he studies how certain neuromuscular responses to prolonged and/or repetitive work, such as muscle fatigue and adapted motor control, are affected by common interacting work characteristics. For example, force, repetition, posture, mental demand, and worker attributes, such as sex, body, composition, and age. We thank Nick for joining us today to present, and we look forward to hearing about establishing acceptable manual forces in the proactive ergonomics process, development and implementation of the arm force field. Over to you, Nick.
Okay, thanks, Catherine, for that introduction. Yeah, it's a pleasure to be presenting this research on the arm force field method, which is essentially a project that was 15 years in the making. And this started back with my master's and PhD advisor, Dr. Jim Potvin, who I'm sure you're all aware of. He actually gave the last CRE-MSD webinar on design, which was a great webinar. So I had the privilege of being trained under him, and this project here with the arm force field method was kind of his inception. But I was lucky enough to work in the lab and was able to kind of carry it through to this to where we have it today. So in terms of the order of the presentation today, I'm just going to talk a little bit about digital human models and ergonomics at first, and then talk about the evaluation of traditional strength prediction approaches, or how things were currently done, or how things have been done up to this point. Then I'll get into a little bit more of the nitty-gritty in terms of the arm force field method and how it was developed and validated, and then eventually implemented within digital human models. And then I'm going to end off with a little more of a practical demonstration of how we can use the arm force field to determine acceptable hand loads. And we made a couple efforts in the last few years to also have this approach integrated within things like Excel spreadsheets, right? So in case you don't have access to a digital human model software, you're able to still utilize the arm force field in some way. So digital human models are essentially a representation of the human body within a digital environment. Okay, so as a technology, it provides a means to create, control, and manipulate human representations within a digital environment. So we can use this in terms of planning optimal work tasks and workspaces. We can adjust different anthropometries. We can look at capabilities in a purely digital environment, which obviously has a couple benefits. And then in terms of, there is a fundamental area of study as well, which goes into creating very high fidelity digital humans, right? So it's one thing to have a good looking mannequin that, looks very realistic, but we also need to make sure that the mechanics and the behaviors of that digital human model is also somewhat aligning up with reality as well. You can imagine that's a challenging thing to do given the complexity of the human body. So why use DHMs? So there's been a lot more applications in the last little while. So we can use it for things like analysis of disorders or surgical techniques, right? We can start to integrate some biomechanical models within these digital human models, right? That comes into play as well for injury analysis, so things like crash testing and impacts. It ends up being a lot of money if you're crashing really expensive cars to do safety tests. Obviously, that's an important step, but a lot can be learned by running those simulations using digital human models as well within a CAD environment. Right? So similarly, we can do product and method testing as well using digital human models. Particularly, the focus within ergonomics has to do with work simulation and process design. So that's a major application. So we can start to consider things like the anthropometric considerations. For example, can a 95th percentile male hand fit into a certain space in order to perform a task? Right? Reach envelopes, can a fifth percentile stature female reach and actually reach the work task that they're doing? These are the types of things that we can actually study using a digital human model before a task ever really exists. In terms of the ergonomics and human factor studies that we can do, we can look at a lot of different things using these digital human models. For example, we can try to predict what the posture of individuals might be when performing a task. We can also look at strength demands, right? What are the actual strength capabilities of humans given a particular simulated environment? And then we can also do other things such as fatigue estimation as well. So it's growing in popularity, the use of digital human models. And overall, ergonomics was traditionally more of a reactive discipline where some sort of injury would be sustained, and after complaints have been made and kind of the appropriate process has been made and compensable injuries occurred, that's typically when ergos would become involved and try to figure out what actually happened and how can we make that job safer moving forward. Proactive ergonomics tries to move earlier into the production cycle. So trying to do our ergonomics assessments before the job actually exists in reality. Right? So if we kind of take this approach, there really are some very large cost benefits associated with this. So in this figure here, we have on the y-axis, a development cost, right? And then on the x-axis, this represents kind of the development phase of a typical product. So I like to give the example of a car here, right? So you have a concept car where it's purely kind of in a concept stage, and then we start to design that more in a CAD environment or computer-aided digital environment. And eventually it leads to the production of actual prototypes and eventually to the first car that's sold on the line. So the idea here is the way that we've typically done ergonomics is once that actual job, that car is starting to be built, that's when injuries start becoming sustained, and we need to invest a lot of money at that stage to try to fix a problem that occurs. Okay, so you can see that results in a large development cost towards the end of a production cycle, right? But the overall goal is if we can adopt a proactive ergonomics process and use a lot of simulation and ergonomics assessments early in the production cycle, so when things don't necessarily exist yet in the real world, right? So if we invest a little bit up front here, that can have a massive implication for the overall cost. Right? If you look at the area under all of these curves, right, the area under the green curve, essentially a lot smaller than the area under the blue curve here, which is a way of looking at cost savings. So I'm going to focus in on the idea of looking at strength demands and capacity, right? And using digital human models in a proactive process to try to estimate what the strength of an individual might be, what the task might require the strength to be, and trying to marry those two together in order to conduct some sort of ergonomic assessment. So let's look at this example of a hose insertion. Right, so most types of jobs out there will require a force or a torque production. Right, mainly more so, I should say, in manufacturing industry, maybe in healthcare even. But a lot of them, it involves your hands, and it requires you to produce some sort of a force. Okay, so from an ergo perspective, we might just say, well, let's make those required forces as low as possible. Right, if that hose just has to go on with a couple newtons of force, that's not going to produce a large demand on the body, right? And it's likely to not result in a lot of injuries. Right? So the only issue with that is if we make those forces so low, we might run into quality or safety issues for the end user of a product. Right? If that hose was installed in a car with a low amount of force, the second the car's turned on, that hose might blow off, the whole car might fall apart. Right? So essentially, if the force required increases, essentially that product failure risk goes down. Right? Okay, so then we can say, well, let's make the required forces as high as possible then, right? Let's design our tasks with the forces very high. But then as soon as you do that, then as you increase the force demands on the individual, they're going to sustain a higher risk of developing a work-related musculoskeletal disorder. So really what we're doing with strengths, demand, and capacity is trying to come up with the balance, right? A balance where we determine an acceptable amount of WMSD risk, but then also determine a force that's low enough that we're not going to have issues with the end product as well. So it's a little bit of a balancing act that we always need to keep in mind. Obviously, as ergonomists, we want to try to minimize risk at all costs, but there needs to be a functional component to this as well. We need to still create products at a reasonable cost in order for society to function. So how do we do this? How do we set force levels so that people don't get hurt? Typically, the threshold that we design for now is the strength capability of 75% of females. And this particular threshold actually derives from some of the early psychophysical work of Stover Snook. And essentially, it was based on epidemiological low back data, where a worker is 3 times more susceptible to low back injury if performing a manual handling task that is acceptable to less than 75% of the working population. So for example, if we look at someone's strength on a normal distribution curve here, what that's saying is if we set a line in the sand here at 25th percentile, that means that 75% of the population will be capable of producing that force. Okay, so the only thing with that is that it means 25% of the population is not capable of that force. Okay, so obviously we would want to design as much of the population as possible, but really what the stats tell us and what the epidemiological data tells us is that this is a reasonable threshold for us to use to really try to taper off that musculoskeletal injury risk. At the end of the day, it comes down to this: injury risk is proportional to demand over capacity. Right? So we need to design a task with a certain demand, but keep that in mind relative to the capacity of the human body. Right? So in our case here, the demand here is figuring out what the actual loads will be on the body, and the capacity is what can the body actually handle. So the way that we've typically looked at strength within a proactive process or using digital human models are using these biomechanical methods, right? Within a lot of these digital human models, so they have their exterior skin or the shell, but inside we have a link segment biomechanical model, which when you posture these mannequins into a given posture, or and then you apply an external load to it somehow, you can calculate through biomechanics what the moments or what the torques are going to be at each of the joints within the body. Okay, so that gives us a sense for what the demand of a task might be. Okay, so that's great. We know what the forces and the moments are in the body, but now we need to compare that to what the capacity of the body is. So we need to do that in order to figure out that 75% capable threshold. So typically, this comparison of demand to capacity, for the capacity side of it, this has typically been done using equations. Right? So there's a lot of strength data for the different joints in the body published in the literature. And we take advantage of these data to try to estimate, in this given posture, this is what we know the elbow strength is, this is what we know the wrist strength is, shoulder strength, and so on. So we were able to make this comparison on a joint-by-joint basis. So practically, so this is an example of Jack, right, which is a fairly common digital human model platform. So, the engineering side of this, the industrial engineering side, the parts can be constructed in this CAD environment or this virtual environment. And then in the proactive ergonomics process, we can place a digital human model, right, and posture that mannequin as best as we think is possible. How would an actual worker perform this task? And then we can evaluate, all right, what's the load that's going to be required by the hand here? So what's that manual force going to be? So that forms the demand side of it. And then we can go to that strength literature and try to figure out what the capacity would be in that given condition. So this process has essentially been automated within the force solver module. But what happens here is, given certain inputs of sex and anthropometry, posture, external force, the software kind of goes through and determines what all those forces and moments are within the body, and then it makes a comparison to predictions of joint strength. Right? It does the same for compression and shear forces in the low back as well, and compares that to spine tolerance limits. But the idea is that we want to come up with a hand load that results in all of the outputs being acceptable to 75% of females. Right? So that 75% of females statistically works out to approximately 95 to 90% of males as well. So in general, in terms of the population, we're designing for the majority of the working population by sticking to this threshold. So typically the way that this would be done is you would start off with a hand load of 0, right? So say the insertion force here, you start off at 0, and then you just keep on iteratively increasing that load higher and higher till eventually you get to a point where one of the joints within the whole link in the kinetic chain of the body reaches that 75% capable threshold. And once that is achieved in one of the joints here, that's what we consider to be our manual arm strength, or the 75% capable strength of the population. Right, so this is how things had been done for quite a while. But in our lab, or in Jim's lab, maybe 7 or 8 years ago, we started to do some testing of that current approach, right, using 3D SSPP from the University of Michigan, and then we did a comparison with Jack as well. And we compared, we essentially brought people into the lab. We measured their actual strength, right, in the up, down, push, pull, left, right directions. So we got them to exert as high as they can, and then we postured a mannequin using the same dimensions as that person, and we tried to figure out, well, what would using this approach back here, what would the software predict strength to be? And we saw a rather large discrepancy in what we measured in the lab compared to what the prediction of the strength would be. And that was for both the 3D SSPP and the Jack. So they both kind of use this link segment modeling, weakest link approach. So that definitely raised some concerns to our partners. A lot of this research was funded by US CAR, which is a consortium of Ford, GM, Chrysler. And it definitely concerned them, because they were using this approach to make a lot of really important design decisions. So we dug into this a little more. So Andrew Hall was a master's student in Gym Lab. And we essentially said, well, you know what, maybe we're not doing a fair comparison because, we brought in our own set of people. Maybe that population just didn't match up with the general strength databases that they were using. So we essentially replicated that same process, right? We figured out what their strengths were in the up, down, push, pull, left, right. But then for each individual, we also measured their individual joint strengths in all those postures as well. So now when we were using that weakest link type approach, we were doing an apples to apples comparison, right? The strength data from that we can predict is essentially matching up with the actual strength data that we measured in the lab. And even though we did this, we were still seeing really large errors. So there's something about this approach that wasn't just matching up with reality. Right? We see manual strength measured in the lab wasn't corresponding with what 3D SSPP or that independent axis approach would estimate. So this kind of set us down the path of kind of looking into what can we do, right? So we identified first what are some issues, right? So potentially the databases that we were using to estimate capacity were outdated or maybe limited in terms of their strength data. the majority of the data used in digital human models and in joint strength equations at that point were from Stobbe in 1982, which is a PhD dissertation. And it's great data, and there's nothing wrong with the data. It's a little bit older though, right? It's approaching 37 years old now. And we know that our population has changed quite a bit in that time. Our anthropometry is different, right? We essentially consider ourselves to be in an obesity epidemic now, right? And it's likely that the strength of the population has changed as well. So maybe that could be an issue. But more so, what's going on and what was kind of validated by that last study I showed you is that in order to estimate manual arm strength, right, trying to find what's the weakest joint when you're producing a force, that relies on multiple joint strength predictions in order to estimate manual arm strength. So with every one of those predictions of joint strength at the joint, there might be some error associated with that. So you kind of get a accumulation of error effect going on, right? So that could be one contributor. And then something else that we kind of got into a little bit and we tried to study in the lab too is just some assumptions that are made that there's an independence of these joint strength axes. For example, at the shoulder, we did a couple studies that looked at shoulder strength. So essentially up here, we had people exerting in the up direction, right? They maintained a static posture as shown here. And then they kind of exerted in the up, and then they went to forward, and then transitioned to down and backward, right? So they kind of went as hard as they could in a circle in this direction. And we realized that kind of the math behind those digital human models is that they would predict strength to be kind of the resultant of two of these axes, right? So it would say that your strength when you're exerting between the up and the forward direction is essentially the resultant of the forward and the up strength. Okay, so we suspected that it would fall more in line with kind of this yellow curve here, right, which is kind of a weighted approach. And what we did measure in the lab is that, empirically it did follow more kind of along the circular path here. So there were very large errors being made between joint axes as well. And then we did another study at the wrist to kind of look at the effect of, if the forearm is pronated or in a neutral posture or supinated posture, can that affect your flexion strength or your wrist extension strength, radial ulnar deviation? Currently, in the previous strength prediction approach, it would assume a straight line, right? So there would be a total independence of forearm rotation on strength, right? So these errors were essentially baked into that approach, right? And these were some of the reasons that we thought were leading to those large errors that we were seeing. So that kind of led us to the point where, okay, we were pretty convinced that there's just something about using that weakest link approach that wasn't quite getting at the value that we want, which is what is the manual arm strength? What's the force that I can design for, right, in order to achieve that 75% acceptable level, right? So as I kind of just discussed, the traditional approach measures and predicts individual joint strengths, right? So it knows your elbow strength, your wrist, your shoulder, and then it increases the manual force until one of those joints reaches capacity. Once that point is met, that's what we consider the manual arm strength to be. Okay, so we said, well, moving forward, if this manual arm strength, if that's the value that we really need to know and the engineers want to design for, they just say, give me a force, Mr. or Mrs. Ergo, give me a force that I can design for, right? So that's what they're after. So what we've thought of is maybe we can develop an approach that we start off with this value here. We start off with the manual arm strength, right? So we empirically measure all these strengths within the lab and come up with an approach that would be able to predict that, right? And then we can work backwards to figure out from that strength value, what is the 75% capable strength? And then if necessary too, we can determine what the limiting joint was within that as well. That might be interesting information for an ergonomist, for example. It could be important. But really what was most important, at least what our industrial partners were telling us, was what's that force limit? What's that force spec? So we set off on a path. This was in 2014. We kind of published the first paper related to this. And what we did, we brought a large amount of female participants into the lab, right? And we measured their strength in the superior, inferior, medial, lateral, anterior, and posterior directions, right? Otherwise known as your up, down, push, pull, left, right, kind of the cardinal directions. So we measured that data for a lot of people in a couple different hand locations throughout the reach envelope. So those are represented by these different color balls here. So essentially we had a cloud of knowledge of what the manual arm strengths were at each of these locations. And then it became a question of, can we predict what the strength might be somewhere in between these locations? Right? Or can we come up with a simple equation that would tell us if the hand is somewhere close to this yellow sphere here, can we predict what the strength would be there? Right? And we showed that using regression approaches, our multiple regression equations, we were able to come up with equations that did a nice job estimating what the strength would be in these 6 directions based on hand location. And that was the only input. We just needed to know where the hand was relative to the shoulder. Right, so this did a very nice job and definitely set us down this path of this being a viable approach. Okay, so at that point though, there was definitely still some limitations. It wasn't a perfect method. It was only applicable to those 6 directions, right? We weren't really sure what would happen if a force direction is required somewhere between the superior and lateral direction, for example. Right? Also, these data are limited by an upright torso, so all our data were collected with an upright torso, so how would things change if the person was flexed forward by 30 degrees, for example? And then the other thing is that it wasn't really validated at this point too, not with external data. So all the data that went into creating these equations, essentially we used all of that data. We didn't really hold back anything to test it. So that was an important step moving forward. And then that's kind of where, I was off. I was interested in, becoming an ergonomist. Jim kind of guiding me down that path. And, they ended up getting, Dr. Potvin, Dr. Kier, Dr. Lyons got a large grant from US Car and Automotive Partnership Canada. Essentially, it was a $1 million grant to try to advance proactive ergonomics. And this was just right down my alley. I love this stuff. And Jim essentially said at that point, I want you to be the arm strength guy. So I remember that moment vividly sitting in his office. And we kind of set down this path. All right, well, let's create a new arm strength prediction method that's going to really, be our best attempt at estimating what these values are going to be. So the purpose of my PhD thesis was to improve estimations of acceptable hand forces, with particularly a focus in digital human models, applying this to digital human models. And the specific purpose was to develop, validate, and implement a novel ergonomics tool for manual arm strength prediction. So I'm going to kind of go through 4 phases of development, essentially talk about 4 to 5 years of research in a couple of minutes here. So the first stage here had to do with developing a comprehensive manual arm strength database. Right, so we did have some of that existing data that I showed you in that previous paper, but there were still some gaps in there, so we needed more manual arm strength data. Right, we needed to, if we were going to create a nice strength database from which we can create all these predictions, we need to have a very robust and comprehensive database. So overall, at the end of all the data collections we did, we had around 95 participants. We measured data at 36 hand locations. The other thing we did was measure strengths in combinations of directions, so not just up and then down. We did combinations of, exerting up and to the right at the same time, or exerting up and to the right and also pushing at the same time. So we really kind of rounded out our data set in that way as well to account for some of those more tricky situations. So here are all the hand locations. We essentially have a nice cloud within the reach envelope. Over 13,000 total MAS trials we measured in the lab. And this is kind of the resulting, all the data. So each one of these cells represents, at least probably 20 or 30 individuals, sometimes up to 60 or 70 individuals. So each one of the cells within here represents a substantial amount of data. You can see that the data spans from those 1D directions, what we call them, all the way to combinations of 3 exertions at the same time, right? And then we have people, different coordinates relative to the shoulder, so they're different heights and forward, backwards, left, right. Okay, so we have a nice comprehensive database now. Now we need to come up with an approach to evaluate multiple regression versus ANN, or come up with a predictive approach that'll be able to estimate what manual arm strength is, given all that data that we have. So essentially, given the inputs of hand location, force direction, torso orientation, right, these are typically the things that you need to define when we're wanting to figure out what the strength demand is going to be, or what a strength capability is. So we want to feed these inputs into some statistical prediction tool. And then after it goes through that black box, we want it to output what the predicted arm strength would be for those given conditions. Right? So essentially, we want to feed those inputs into a black box here. Underneath the black box, that was either going to be a multiple regression or some sort of other statistical model. And what we ended up going into was the use of artificial neural networks, right, which is essentially a machine learning technique, which is obviously gaining a lot more traction now. A lot of studies are incorporating machine learning within their analysis. So this was, relatively novel at the time, in terms of strength prediction in ergonomics. The idea here is that, we have our desired inputs of hand location and force direction, and then we can train this network or this statistical model to figure out the relationship between those inputs and an output, which in our case was strength. Okay, so the way that it works is you kind of take a big portion of the data that you collected and it's called training the artificial neural network. So we trained a model to essentially realize the relationship between those inputs and outputs. And then we withheld some of the data too in order to test this model as well. So what we did is we wanted to just do a simple study comparing the multiple regression approach versus these more complex artificial neural network models. Right, so just kind of long story short here, these blue dots represent the regression approaches, which obviously still pretty good representation, pretty low errors relative to what we were seeing before in using the traditional approach. And then when you compare that to the artificial neural network, you can see that it does a very nice job. So that kind of the more faint circles there represent the development data or how the model was trained. And then the validation data represent data that weren't actually included in its development. So the model was doing a nice job predicting arm strength for conditions in which we didn't actually use it to develop the model. So long story short here, this gave us a very good sense for the approach we wanted to use moving forward. This artificial neural network was definitely seeming to be a powerful method for us to use. Okay, so from that we were able to choose the best approach, and then the next step was, okay, well now let's optimize and try to find the best possible algorithm for this application. And eventually what that ended up producing was what became called the arm force field method. Right, so arm force field is essentially a name that me and Jim came up that represents manual arm strength based on only hand location and force direction. So wherever the hand is relative to the torso, we're able to predict essentially what forces you can generate in any possible direction. And you can see this kind of mimics that black box, right? The arm force field method is that black box. So we have those inputs of torso orientation, hand location, and what direction are we going to apply. That gets fed into the black box here, and we're able to predict the manual arm strength for a given percentage of the population. So just kind of very briefly to just summarize how it works. The first thing is, given those inputs, we still had that issue of collecting all our data in an upright torso orientation. So one way that we dealt with that is we kind of figured out, if you are flexed over a little bit, what is the weight of the arm, right? And is that weight of the arm actually adding to what the strength would be, or is it taking away? So for example, if you're exerting in the down direction, you're able to use the weight of your arm in order to enhance the force in that direction. In comparison to the up direction, you actually now have to overcome the weight of your arm first before you can start to apply a force in the up direction. So we essentially used this principle in order to figure out what the strength would be. We called it in a zero-G environment. Right? So just what is the strength independent of the weight of the arm? So we were able to kind of account for that. And then we use that within our manual arm strength artificial neural network. In terms of the network that we selected, we kind of went through a rigorous process to try to figure out what's the best architecture, what parameters can we use that gives us the best balance of high predictive ability, but also a large amount of validity too, right? Because the more kind of layers that you have within that model, the more complex you make that neural network, essentially the less likely it is in order to kind of overfit the data, right? It's going to just kind of do its best to map out what the strengths are, but it won't do a good job reproducing a strength. So for example, if you try to estimate a strength in a condition for which we didn't have actual data, it would give you a pretty large error. It wouldn't do a good job estimating it. So long story short here, we went through a rigorous process to try to test and find the optimal architecture and are comfortable. We ended up with a hidden layer of 13 nodes and a couple other parameters. But probably the most important part of this had to do with the validation as well, right? So we kind of geeked out on a lot of this stuff to try to figure out the best model and, doing a lot of MATLAB coding to try to figure out what will work best. But at the end of the day, we needed to make sure that our model was going to do a good job estimating strength in conditions for which we didn't have data, right? It needed to be a robust, reliable model for arm strength. And that's being shown here by the test data, right, in the blue diamonds here. So those data weren't included in the official development of the neural network, but when we tried to use our neural network to predict what the strengths would be, they did a very nice job matching up like what the measured strength was versus what the predicted strength was. So overall, this seemed to be quite a valid method moving forward, and that's kind of a way to statistically test it. But we also did a whole bunch of testing in terms of does this thing pass the sniff test as well, right? So one example we did that really kind of proved the efficacy of this method was say you take these shells around a person. So this would essentially represent the reach envelope, right? As you move further away, kind of that reach envelope kind of increases. But so what we did was a couple testing. Well, if you take this shell here, let's call that 40% reach, and then you flatten it out, do we have nice smooth transitions in strength between it? So here, this is showing anterior strength, right? So that would be kind of pushing in the forward direction, right? And you can see that what this represents is the hand right directly out in front of the shoulder. You can see that you're generally stronger there, and then there's a smooth transition away from that as you kind of rotate the arm away from there. So the important thing to see here is the nice smooth gradual transitions in the heat map plots here, right? In terms of looking at the different directions, so here I'm going to go from 40% reach, and then I'll go to 60%, and then 80% reach, right? And then these represent those 6 cardinal directions too. You'll see as we kind of increase the reach distance, we have a nice transition in how the strength changes between those. So I'll kind of go back and forward. You can get a sense for nice smooth transitions in these areas. So that gave us it was a nice face validity check for how our model was performing. Okay, so overall to summarize, so essentially the research was, a big component of it was just developing the method and validating it. That's kind of summarized here on the left side here. But then the next part of this too was, we were sponsored and funded quite heavily by industrial partners. And, I'm sure, they wanted to fund basic research as well, but at the end of the day, they wanted a product that they could use, right? Something that they can incorporate within their design process to, at the end of the day, reduce injuries, right? So an important step to this was coming up with a way to implement this neural network model or the whole arm force field within digital human models, right? So with a digital human model, we can use all those inputs that we need, right? Like we know what the hand location is and the force direction is and the trunk orientation. So we have the inputs into there. So now we're able to integrate the arm force field kind of within the data stream of these digital human models. And using that, we're able to figure out what the manual arm strength would be. There was a couple steps we had to build into the process, which are essentially our checks as well. And we could correct for the percentile as well, just so we could end up with that 75% capable value. And then also we collected all our data on females. So you can also apply a correction factor if you want to predict the strength for a male as well, just based on average differences in upper extremity strength between males and females. So overall, that was kind of the process, the research development and implementation process. Overall, it was a large project. Essentially, it spanned 15 years, started with Jim, even at the University of Windsor. Myself, several other HQP or researchers within his lab. It ended up producing 6 to 8 peer-reviewed publications related to the arm force field method. So one way, to what this is saying, and that it's been extensively evaluated by our scientific peers. We've presented it extensively too at over 12 conferences, and then we've worked with some of the digital human model companies as well to integrate the arm force field within there. Right, so Santos Human has it integrated within, Jack has it, and Human Cat as well. So that was an important step for us to, not waste all this valuable research and just have it sit in a paper that gets read a couple times a year. We wanted to make sure that this research product was actually going to be used by practitioners. Okay, so of course, with any modeling approach, there's always going to be some limitations. So one overall limitation of the arm force field method is that it only considers arm strength capability. Right? So what we mean by that is that it doesn't really consider other biomechanical limiters of strength. For example, balance, right? The arm force field doesn't really take into account what the whole body balance state of the individual is. Right? Also, maybe the lower extremity strength might be an issue when you're producing these forces, or hand strength or grip orientation. So these are things we're starting to tackle now individually, and what I'm starting to look in my research lab now, as I start off on my own research here. And essentially, the thing is, most of the DHM software can handle a lot of these analyses. So the overall philosophy now is, okay, well, let's figure out what the arm strength is, irregardless of all these other limiters. Okay, and then once we know that, well, let's figure out, is balance going to reduce that by a certain percentage? Or maybe, okay, it's great that we can produce a force of 50 newtons. We deem that to be acceptable. But maybe due to hand strength, we can only get away with 40 newtons. Right, so the idea is that we can figure out what the arm force field strength is, and then correct from that point on if we have some other potential limiters for that strength. Right, so I'm continuing to study that moving forward and trying to integrate some of this stuff within it. But still, overall, this is a way that we can get around it right now. Okay, so I'm going to go through an example now of actually using the arm force field method. Okay, so as I said, we need a couple inputs of hand location, force direction, arm posture. And say the question here is a lifting force of 45 newtons acceptable to 75% of the population? Right, so we would use those inputs now, feed it into our arm force field method, and what this would tell us is that for these given parameters here, the acceptable hand load is 89 newtons. Right, so when you compare 45 newtons, which is the demand, to 89 newtons, which is the capacity, this would tell you that the task would be acceptable to 75% of the population. If, for whatever reason, the arm force field tells us that the acceptable hand load is 40 newtons, right, that now is below what the actual task is requiring. So that means in terms of our demand to capacity balance, we would consider this task to be not acceptable. These are essentially how the arm force field is being used in practice to help make ergonomics decisions. So here is the arm force field integration within Santos Human. So essentially, you can posture your mannequin however you'd like. You can apply forces to the hand, and then pull up this arm force field module. Right. So let's look at that previous example. Right, our 45 Newton force. So you'd enter that in, and then you would run it, estimate arm force, and that gives you a prediction of 89.1 newtons. So that's saying that the AFF predicts a one-time strength of 89.1 newtons. The other piece of information that tells you is that that task is acceptable to 97.7% of the female population. Okay, so that gives you the one-time strength, which is important knowledge. But what if we get into these scenarios? It's not very common in any workplace where you're going to exert one force and then be done for the rest of the day. Usually there's some sort of repetitive component to any type of force exertion. So for example, if we have a frequency of 12 efforts per minute and a duration effort of 0.7 seconds, so every effort you do lasts 0.7 seconds. Right, so that means that there's some repetitive nature to this that we're going to have to account for, because as you keep on doing things repetitively, there's going to be a certain amount of fatigue that's going to start to reduce your overall ability to produce force. So to account for this, we actually go to Jim Potvin's prior method known as the maximal acceptable effort equation. So using this approach, he essentially compiled a bunch of psychophysical studies and data, and he found that for a given duty cycle, or the percentage of time that you spend in exertion, right, relative to overall time, So he built a relationship estimating what the maximum acceptable effort would be based on duty cycle. Right? So it kind of follows this curve here. And so that means if you're doing a task that has a very high duty cycle, you need to only recommend a force limit somewhere between 10 to 20% of your maximum acceptable effort, or what the strength would be. So we're able to use this. This equation's been, cited quite a bit since that time. Originally, it was designed with upper extremity data, but it's been validated as well in lifting data as well. So this seems to be a very robust equation to estimate how we can adjust our strength based on duty cycle. So how we would use this in terms of the arm force field is, in order to use this, you need to figure out, well, what is that 100% level, right? What is the overall maximum acceptable effort anyways? And that's what we can use the arm force field for. That gives us what the one-time strength is, right? So once we have that 100%, then we can use our duty cycle to figure out and multiply that by the arm force field strength, right? And based on that, we can figure out the acceptable force, which is now corrected for repetition and duration. So maybe just to kind of help clarify this, I'll show one more example, right? So I'll show that data we had before. So a frequency of 12 efforts per minute, and each of those efforts took 0.7 seconds. So we can plug that into to calculate duty cycle, right? So if we do that, we figure out that the person is exerting with a duty cycle of 14%. So if we look that graphically here, right, you can plug those numbers into the MAE equation as well. What that tells you is that given these frequency parameters, the person shouldn't be exerting above 38% of what their maximum is. Okay, so this is how this is applied to the arm force field method, particularly within digital human models. Right, so practically within here, we have our 45 Newton force. You can enter some of the inputs there for cycle time and frequency and duration. It'll automatically calculate your maximum acceptable effort. Okay, and essentially what it does at that point is multiply the 38 by what the arm force field strength was, which we know from before was 89.1 newtons. And now that gives us a corrected strength now based on frequency. So given that example before, this would now be unacceptable at the current duty cycle, right? Our 45 Newton load is above what we would deem to be acceptable. So this is how we can go through and actually use the arm force field practically. So this has been integrated within Jack as well. So they have a little bit of a different dialog box here, but essentially it's going to kind of compute the same type of information there. Okay, so that was our main focus when we were doing the research, right? Integrating this stuff within digital human modeling and for it to be utilized in the proactive ergonomics process. But then, we had a lot of practitioners saying, this is great data. I have lots of ways that I need to know strength sometimes, even relatively. Like, are we stronger if the hand is out in front of the body compared to when it's 45 degrees rotated from the front of the body? So based on this, we created a couple lookup tables for manual arm strength as well. And we published this in Primus in 2016. Right, so based on kind of inputs of vertical angle of the arm and then horizontal angle, we came up with a couple lookup tables here where you can go through and figure out what the arm force field strength would be. So here we have female 25th percentile manual arm strength. That would be equivalent to our 75% capable. Okay, and then we did it based on reach as well. So closer to the body, somewhere in the middle, and then we also have another grouping of tables for a further outreach. So it was a way to kind of access some of these data maybe a little more simply without needing a digital human model. Okay, if anyone wants to kind of look at the code for this too, we produce a MATLAB code. This is all open source and available. Okay, and then kind of what we're excited about now, and I have to give all the credit to Jim with this because he spent a lot of time coding in the arm force field into an Excel spreadsheet as well. And we have this now at the point where all you need to do is enter in kind of the yellow boxes here are the inputs. So you can enter in where is the hand relative to the shoulder, right? So how many centimeters is it to the right or to the left, or how far is it up or down relative to the shoulder? So you enter in that information, which is something you can easily measure kind of using some some side of like a ruler or a tape measure. And then you have to tell it, well, what are the forces in the left hand? What's the force in the right hand? Okay, so you can enter that in either as a unit vector, right? So -1 being in the inferior direction, +1 being in the superior direction. Or you can actually enter what the force is, right? So if you want to do an up strength, you're evaluating a strength of 50 newtons, for example, you can just put 50, 0, and 0 here, and it'll automatically calculate what the strength would be in that situation. Okay, so this was something, if anyone's interested in the spreadsheet, or for any of the materials that I've touched on today, I'm happy to just send me an email. I have my email address here. And we've kind of created a nice package of the papers, the published papers that went into this, as well as some of these tools, including the spreadsheet here.
Hi, Nick. It's Catherine. So we have about 1 minute before we open it up for questions, and it's perfect because you're conclusions.
Okay, yeah, last slide here. So overall conclusions are the traditional way of estimating manual arm strength. You know, we did a lot of research on that, and it seemed to be problematic. It wasn't really doing what we were hoping it was doing. So the arm force field method represents an approach to estimate strength capability that kind of circumvents some of the prior limitations. And you know, the original intention was to utilize this within digital human software. And to be honest, that probably is the best and most complete utilization at this point. But we're starting to produce some other methods as well that makes this even more accessible to the general practitioner. So with that, I definitely thank you for your time and attention, and definitely happy to take some questions.
Thank you so much, and I see people are typing, so as we're waiting for these questions to appear on the screen, I'll kick us off. Your duty cycle, I'm really, really excited about that and its application, and I'm thinking about our client-patient handling community of practice. What do you think are potential applications for this to help us prevent MSDs for client-patient handling?
Right. Yeah. So healthcare industry is definitely huge. Like they can definitely benefit from these types of analyses, and you know, simulation in general too, because the you know, healthcare type studies and patient client handling can be difficult to study from an ergonomics perspective. It's tough to understand what are the forces that are being applied, right, when you're handling an individual. So this actually lended well, and Jim Potvin, again, I keep bringing him up, but he actually, I think, published some studies recently looking at patient client handling as well, and essentially used one of the digital human models to essentially simulate what those interactions would be, and use the arm force field as part of that process as well. Similarly, Dr. Steve Fisher at Waterloo, he's doing a lot of work on first responders and paramedics, and that's another type thing where he was able to kind of use simulation and the arm force field to estimate what the strength demands are in those difficult situations to study in the lab. So yeah, I mean, healthcare is definitely one place that we can utilize.
Thanks so much, Nick, and also for those references to those researchers. So we have a few questions here, one from the automotive manufacturing field. I'm curious as to how the arm force field would work with the aging workforce. We have young workers as well as those who've been working for 25 years.
Yep, this is a really good question, and it's something that needs to be dealt with. It's something that I plan to study actually in the next couple of years. We know that in general, strength tends to decline towards the later years of life. You know, from 30 to 40 on, we start to see a general decline in strength as you continue to get older. And that isn't really being accounted for now in many ergonomics tools. So that's in general kind of an ergonomics problem that we're all having to work with. You know, one way that if this is a real concern for you, I guess I should say, I didn't say it in the presentation, but the arm force field was developed using a sample from the whole population. So we got people, it's been a couple of years now, but essentially like 18 to 30, then 30 to 50, and then 50 plus as well. So we kind of representatively sampled that range of the population. We didn't just cherry pick young people, and that's where all our data came from. So
it's helpful to know.
Yeah, I should have mentioned it in the talk there. But that being said, if you have a plant that has primarily older workers or a plant that has primarily younger workers, if that's something that you want to do, you can always look to the strength literature and try to come up with your own correction factor there. But really, it is something that we should start studying in the labs, and it's something that I'm planning to do in the next little while.
Thanks, Nick. That also came up in Jim's presentation as well. We have a question here. Do you have any insight into where AFF and original DHM strength models differ? Locations in space, specific directions, and if so, does AFF tend to predict greater or lower strength than original DHM models with these parameters?
Yeah. Oh, thanks, Kip, for the question. This is something we haven't really looked into, but I think I was at a US CAR meeting recently. It's something that I think they did and they looked into, and it definitely was different, right? But that more speaks to kind of the large errors that were made before. And it kind of boils down to, we can't really trust the predictions based on all the research we've done. We can't really trust the predictions that were coming out of the prior ways of measuring strength. So, if we're measuring above or we tend to be below, we don't know if that truly means anything at this point. For the most part, from what I remember when we were looking into it, it tended to, like the prior method tended to overpredict strength relative to what we were finding, which is certainly a bit of a concern, right? Because they were kind of overestimating strength capability. So I don't know, that thing, I'm not sure if it's really been studied at direct comparison, but either way, it's tough to make that direct comparison because essentially it was a pretty random prediction. If you go back and look at the correlations and the errors, that we measured with 3D SPP and JACK, kind of the prior method compared to what we measured.
Thanks, Nick. And finally, I think this would be our last question for today. The drawback to software to date has been the estimate of cumulative stress due to actions in more than one motion. Can your work overcome this?
Yeah, this is again one of those kind of big challenges in ergonomics that we're trying to overcome now. Trying to account for cumulative loading in the body. And right now, kind of the best thing that we can do is kind of do those frequency corrections based on psychophysical data. There is a lot of good work now coming out of Sean Gallagher's lab at Auburn, where he's trying to account for cumulative loading within the body, particularly relating to manual arm strength. It's something we can't really look at right now in terms of kind of what's happening at the tissue level within all this. But again, I'm just starting off my research career now as an independent researcher, so all of these ideas from practitioners are very interesting to me and things that I want to continue to study over the next couple of years.
Thanks, Nick, so much. And just, we had another question pop up and we still have 2 minutes. So are you planning on teaching this to the ergonomic professionals in the auto industry?
Yep. Oh, Emil, thanks for the question. We actually know each other. He taught me quite a few years ago. Yeah, so this is definitely being incorporated within the automotive industry right now. We were recently at a US car meeting where, this is definitely part of the process for a lot of the engineering group within the automotive companies right now. So in terms of like a one-to-one teaching ergonomic professionals, a lot of this is actually getting taught too at the university level. So those people who end up graduating from our universities and colleges who are moving into ergonomics roles now. We're pretty much across the board now in at least Ontario. We're incorporating a lot of these analyses within the education. So I think you'll start seeing now as those students now are starting to become ergonomists in the automotive industry and any other industry, they're going to have more of a working knowledge for some of these proactive ergonomics tools. And I think that's only going to help the overall adoption of this stuff.
Nick, I want to thank you so much today for your presentation, and I think having this presentation after also having a presentation previously by Jim was a smart, although not calculated move on our part, because it really pulled together a lot of integration of learning from one presentation and then your application. So it was great, and I see our participants are saying thank you, great presentation. Thank you again, and thank you to our participants for joining us, and please Continue to watch our events page. We do have a client-patient handling webinar coming up next week, and we hope to see some of you join us. Have a great Thanksgiving, everyone. Thank you.
Thank you.